So we will continue from where we left off last time. We talked about quantization. And after we quantize, how do we go to a digital signal? Well, the first step is to encode the quantized output. Now, this is a way of representing the quantized real values by a discrete set of numbers. And there are different ways of doing this. There are different codes which perform differently in the presence of errors. Now, first of all, let's see a very, very natural, maybe the first thing that comes to mind, which would be the natural binary codes. Let's use this. Okay, so suppose we have 16 quantization levels, x1 through x16, x hat 16. Now, with natural binary coding, we would start from 0, go up to way to 16 using binary numbers. Okay. However, notice that with these numbers, the difference in terms of the number of bits that are flipped between adjacent levels is small. Now, imagine a communication system where some bits get corrupted. Okay, it is much more likely for one bit to get corrupted than 2 bits being corrupted at the same time. Okay, now in the event that a bit gets corrupted, we will go from one level to another. I mean, we will go from one quantization mapping to another quantization mapping. The idea is it will be best if the quantization mapping that we go to is close to the actually correct one. So for that, it would be good if between adjacent levels, the number of bits that differ is not too much. I mean, that is, if the number of bits that differ is a lot, okay, it is unlikely to make that mistake. So it is okay if the corresponding quantization levels are far from each other. But between adjacent levels, right, since the error is not too bad between adjacent levels, we would want to reserve the high probability of error between those levels. So that is why, so if, for example, if you look at the natural binary code, it doesn't really quite satisfy this, because between x2 hat to x3 hat, between level 1 and level 2, 2 bits differ, right? Between level 3 and level 4, 3 bits differ. On the other hand, with just a 1 bit difference, you can go from level 3 all the way to level 1, or worse, from level 3 all the way to level 7, which would be a critical error in terms of distortion. So that is why gray code was designed. If you look at the gray code, from 000, we go to 0010. The difference is 1 bit. From this, we go to 0011 and then 0001. So between adjacent levels, we keep this only 1 bit difference. What is the benefit? Highly likely error events lead us to small distortion. Okay, that's why gray code exists. Now, let's talk a little bit about pulse code modulation, which is one of the oldest waveform coding mechanisms. It's a way of taking a whole waveform and converting it to bits, essentially. Okay. Now, suppose we use a pre-sampling filter, in other words, an anti-aliasing filter, to limit the input to some bandwidth W. And then we sample at rate 2W. Okay, suppose also that the maximum amplitude of our signal is limited by a certain value x max. All right, so x of t comes into the sampler, and we get these real values. These are quantized and then encoded. This is PCM. The result is a PCM coded binary signal sequence. Now, the encoder for every sample outputs a binary sequence of length v. Okay. Now, if binary sequences are of length v, as you know, this corresponds to 2 to the v different levels. The total range of numbers that we are quantizing is minus x max to x max due to this condition. That's the largest range that we are allowing the signal to occupy. So we are dividing a range of 2x max to 2 to the v levels. Hence, our quantization resolution is delta 2x max over 2 to the v. In PCM, the number of quantization levels is typically high, so it may not be a terrible assumption for a lot of signals that the quantization noise is approximately uniform between quantization levels. With this assumption, the distortion and SQNR computation is relatively easy. As you know from last time, distortion is the expected mean square error between the actual signal and the quantized level. Okay, so the expectation of this is now these errors live between minus to plus delta over 2 because our quantization intervals are of size delta. The difference lies between minus delta over 2 to delta over 2, and we assume the error is uniform. So the error is uniformly distributed from delta over 2 to delta over 2, and we know that the variance of that is delta squared over 12, and the mean of that is 0. So now we can substitute delta, right, as 2x max over 2 to the v, or 2x max over n. So 2x max squared over 12 is 2x max over 3n squared. Okay, hence the signal to quantization noise ratio SQNR, there's a misspelling here, is P max x max squared over 3n squared, which is 3n squared P max over x max squared. So the signal to quantization noise ratio improves quadratically with the number of levels as expected. P max is the signal power or expected value of x squared. Okay. Now, P max over x max squared is clearly less than or equal to 1. This means that our SQNR is upper bounded by 3 times n squared. But n is 2 to the v, n squared is 4 to the v. So our SQNR is upper bounded by 3 times 4 to the number of quantization bits. So if you take the logarithm, you'll see that 4 to the v corresponds 6 dB times v. Okay, v times 6. So each extra bit increases the SQNR by 6 dB in PCM. Okay, let's do a numerical example. What is the resulting SQNR for a signal uniformly distributed on -1 to 1 when uniform PCM with 256 levels is employed? First of all, 256 levels means v equals 8. Okay, Signal uniformly distributed from -1 to 1 means 2 squared over 12, 1 over 3 is the signal power. Okay? So using x max equal to 1, okay, the SQNR is exactly, not upper bounded by exactly, because we can use this formula now. SQNR is exactly equal to 3 times 4 to the V times 1 over 3, which is 4 to the V, which corresponds to 48.16 dB. Is that clear? So how about the bandwidth requirement for conveying PCM sequences, for sending PCM sequences? The bits per sample times samples per second computation gives us 2V times W, because V times 2W. 2W is the number of pulses, samples that we're taking per second, and we need to send exactly those samples by encoding them in PCM. So 2VW. Now, you do not, I mean, we have not proved this, but we can see that we can roughly argue that the minimum bandwidth requirement for binary transmission, I'm not saying any other, making any other claims on any other coding technique, at rate R is R over 2. Okay, in terms of the number of dimensions per hertz. Okay, so now then we need we have 2 VW bits per second, bits per second, divided by 2 bits per second per hertz. That's the spectral efficiency limit for binary transmission. And as I said, you can just take that for granted for now. That corresponds to V times W as the minimum bandwidth requirements. What does that mean? If the bandwidth of our source is W and we are encoding with V bits, okay, we're going to need V times W bandwidth for transmission, binary transmission. Okay, pretty simple. Now, how about non-uniform PCM? Now, with high V, we assumed that quantization noise is uniform. However, it's not exact, and this assumption may not hold if V is small. What do we do in those cases? We could take the signal itself, original signal, and kind of uniformize it. Okay, uniformize it. How do we do it? Pass samples through a nonlinear element that compresses large amplitudes so that it kind of reduces the dynamic range at large amplitudes. And then we can feed this modified signal to uniform quantization. And after recovery, reverse the compression operation at the receiver. This is called compression, followed by expanding and shortened as companding. There's a standard mu law compander for speech. The reason for the mu comes from this parameter mu inside the nonlinear function that is used to compress. So if you look at this function for the mu law, if x is the sample value, the output of the compander is g of x. The output, I'm sorry, of the compressor is g of x, and g of x is logarithm 1 plus mu times the absolute value of x divided by 1 plus mu times signum x. if you plot this function for different values of mu, for mu equals 0, it is the identity. For mu equals 5, you see that it is has a high slope at low values and a low slope at high values, which corresponds to reducing the dynamic range at high values. When mu increases, the mu law becomes more and more active. This is used in telephony systems, for example, classically PSTN telephony. So if you look at the system diagram, samples are fed into the compressor, nonlinear device, nonlinear essentially computation. They are given into a uniform PCM encoder. Those binary sequences are decoded, meaning mapped back to the X hat values, and the X hat values are fed through the inverse transform. Okay, and after the inverse transform, if you want to go back to analog, you can use a reconstruction filter. There are other laws that are possible for these compression and expansion. Depends on the taste of the user. A law, for example, has such a characteristic. Sharper, sort of, at both law. Sharper for A equals 87.58, maybe smoother for A equals 2 than the law. Okay. For speech coding, for example, one could prefer mu equals 255. Suppose we use the uniform quantizer then, following the mu law, with 128 levels. Speech is typically limited to 4 kilohertz. Okay, so if we sample at 8 kilohertz, that's fine. That gives us a sample duration of 125 microseconds. And in terms of the rates, 8,000 samples per second, 8 kilohertz corresponds to 8,000 samples per second at 7 bits per sample. Well, that's 56 kilobit per second. Remember V times W, 7 times W, right? That requires a channel of bandwidth 56/2. You may remember, some of you may remember 56 kilobit per second from older modems. Now, so far, we very naively described PCM as take the samples, quantize them, encode them. But isn't it sort of lossy when we're talking about a signal variation in time, right? And from one value to the next one, for example, 125 microseconds later. Do we want to really consider this new sample as something that we're seeing for the first time? Or do we want to see it in relation to the previous sample? Because chances are, it is related to the previous sample. So what if we encoded the difference between the samples? Well, then we would expect a dynamic range which is much less, right? So that's a really brilliant idea, and it's not very hard to arrive at. Of course, most signals that occur in real life are correlated in time. Okay, they have some kind of memory. So if we encode the difference from the previous sample to the next, we will be encoding a smaller dynamic range. Hence, remember, SQNR is related to the dynamic range, right? In relation to our number of bits. Now we can get better performance for the same number of bits per sample. A very extreme special case that is very, very popular actually in modern communication systems, surprisingly, is delta modulation. which uses only a 1-bit quantizer. Okay, what is a 1-bit quantizer? What can it do? It just gives us up-down comments, right? It says, so basically it's 1 bit, so it's giving us 2 possibilities, and those can be, well, go up or go down, the signal increased or decreased. Very easy to understand and very easy to implement, by the way. So input signals samples come in here and they go through the 1-bit quantizer, which gives us ones and zeros. Clearly, if you pass the ones and zeros through the integrator, you obtain an estimation of the signal. Now, if you obtain an estimation of the signal and compare with the new incoming signal, you can decide whether it's up or down. Very easy. When you low pass filter the integrator result, just like, remember the staircase function of the sample and hold. If you pass it through a low pass filter, you'll smooth it out, and that's your analog input. Very easy system. Okay, now this is a description of delta modulation. Remember, if you see here, the signal rose very rapidly from time 0, but the delta modulator is struggling to catch up. The integrator output is struggling to catch up. So if we maybe made the delta smaller, if we made the number of samples per second more, or if we made delta smaller, things will change. But this delta is quite large, and it is catching up fairly quickly. However, look at this duration where the signal variation is slow. Signal doesn't vary much, but the delta modulator output has to give us zeros and ones. So it is going to oscillate, although the signal is not oscillating. So this is called granular noise caused by the large delta. On the other hand, while we can reduce the granular noise when the signal is stationary with small delta, this would cause the catching up of the signal to be slower when the signal changes fast. So this is called slope overload distortion. So there's a trade-off, as in everything, and this is, one technological solution is use adaptive delta modulation, where you adapt the step size delta to the slope of the input signal, of course. Now let's talk a little bit about time division multiplexing now that we have PCM, because time division multiplexing is a natural extension to waveforms that are bit sequences that are obtained by PCM, especially in older classical telephone systems like the public switch telephone system. What is TDM? Time division multiplexing. Now, a given time interval t sub 1 is selected as a frame, okay? And each frame is subdivided into n subintervals of duration t1 over n, where n is the number of users who are going to share this frame. These are called time slots, if you will. Each subscriber who wishes to use the channel for transmission is assigned one of these subintervals. Okay. Now, in PCM telephony, each user will transmit one 8-bit sample in each subinterval. Remember, we made the computation and we arrived at 6 kilobit per second. That's the one. Each subscriber transmits one sample in each time slot, in each subinterval. Okay, and the combined signals of the users are multiplexed together in a frame. Okay, earlier we talked about FDM, and this is very similar. FDM is multiplexing in frequency. This is multiplexing in time. Often FDM and TDM are combined in communication systems. Now, in digital speech transmission over telephone lines, there's a standard TDM hierarchy. In the first level of the hierarchy, 24 digital subscribers are multiplexed into a single data stream of 1.54 megabit per second. 24 times 1.54, right? I'm sorry, the whole thing is 1.54, which is from 24 times 64 kilobit per second. What is a 64 kilobit per second? 56 plus overhead. Okay, so and there are a few additional bits for control. The resulting combined TDM signal is called a DS1 channel. In the second level of the hierarchy, 4 DS1 channels are multiplexed into a DS2 channel, each having a bit rate of 6.3 megabit per second. Okay. In the third level of the hierarchy, 7 DS2 channels are combined via TDM to produce a DS3 channel, which has a bit rate of 44.7 megabit per second. So this is a picture representing what we just said. Each of these subscriber lines, digital subscriber lines, are coming in, multiplexed to 1.5 megabit per second, and then multiplexed again with other DS1 units, 6.3 megabit per second, and then multiplexed again. In the third level, they reach to 44 megabit per second. Okay, fourth level, fifth level, etc. Now, that was public switched telephony. TDM is used all across communication systems. Examples, other classical examples are the second generation cellular communication system, GSM, and the third generation cellular communication standard, GSM Edge 3G. Of course, TDM exists in LTE as well, in different form. And of course, it's going to exist in 5G, and TDM is there in Bluetooth and many other technologies. Now, in wired networks, optical networking, for example, SONET is the synchronous optical networking transmission standard used in backbone networks. It's based on TDM. There are TDM buses in many wired systems like cars. Okay, in cars, still many things are wired. Many of the communication between the sensors of a car is through the CAN bus, which is wired TDM communication based. In cellular networks and wireless LANs, especially wireless LANs, like 802.11 based Wi-Fi and 802.15 based Zigbee type systems, we prefer statistical multiplexing because users come and go at random and users have data demands that are random. Think about regular telephone, for example. When you pick up the phone, you intend to talk, right? So you intend to produce a stream of packets at a relatively constant rate. And when you're done, you hang up, okay? So there's not much variation. There is not much burstiness. Especially, of course, there is some burstiness among syllables, and there are some silences and pauses in speech. But it's relatively, once that flow is on, it is on. It is not like that in Wi-Fi. In Wi-Fi, when my phone is on, sometimes an application sends a request or update, and sometimes it doesn't. Sometimes I want to take a look at a picture, and then I put my phone down. So the users come and go. Relatively, they are each active on a fraction of the time, but they're uncoordinated. You cannot simply just assign time slots to users. It would be an inefficient use of your bandwidth. So that's why in this type of data-based settings, okay, especially also in machine type communications, which means data that is generated for tracking or other real-time applications or localization updates, etc. TDM may not be the best technology of choice for efficient use of the channel. We use something called statistical multiplexing, which means basically assign the channel to everyone, and they use it on they access it randomly. There is something called an Aloha protocol, which maybe we have time, we can discuss it a little bit. Basically, it is based on users trying to use the channel when they have data, and if there's a collision, they back off for a random amount of time. And this is the idea behind the Ethernet protocol, which is used in wired networks. In our university, for example, there are Ethernet jacks on the wall that you can plug your computer into. And the wireless Ethernet standard is used everywhere in, on our routers, Wi-Fi routers, right? So those are not essentially TDM based, but statistical multiplexing based. Now, from TDM, regular telephones have already migrated to voice over IP, by the way. Let's note that down. Those of you who are interested can read further on source encoding topics. You can also read about sigma delta modulators, which is a more sophisticated way of coding, speech coding. You can read about the JPEG image coding standard in the textbook. There's a quite nice part on that. And I would also suggest that you read about the Huffman source coding algorithm. But